Welcome back. So let's see quickly what are the different faults which we have been talking about: the reverse fault, thrust fault, a normal fault, and strike slip fault, and then see how the surface manifestation are been seen on the surface. So style of deformation, this we already discussed, that we have three type of deformation usually has been seen on the globe. So one is in extensional tectonic environment, compressional, and shear, and respective deformation pattern or surface expression has been given here, that you will have the one block is moving down with respect to another in this case the reverse, the block moves up with respect to the another block, and then the block is displaced horizontally along the strike. So this shows clearly that you have the initial, I'll just play it again. So you have the movement which is taking place along almost a vertical fault and resulting into the strike slip one. So the feature which has been shown here has been displaced. So this was aligned earlier, but now after the movement along this one, you see that they are sitting apart away from, and this is the man-made structure which has been shown here. So if this type of movement has been seen, then we mostly classify this as an strike slip fault. Okay, so strike slip fault that accumulates horizontal slip between the adjacent block. So in another case, in extensional tectonic environment, what we see is the one block is moving down and another block is the stationary block. So you will you can easily make out that that which block has moved down if you have exposed this section here. Otherwise, as I was talking on in one of the lecture, that if you have the surface expression something like what you have, because after the erosion what you will see over here is just an warped surface. Okay. So you may look at the surface expression something like this. Now the question remains that which type of faulting was responsible for the scarp. Okay, it may be this dipping. If we say, let's say this is north and this is south here, then it may be due to the north dipping fault, or it may be due to and south dipping fault. Okay. But in this case it will be a normal fault, and in this case it will be a reverse fault. So on the surface both the scarp both the faults will show a very similar topography. So this we will more clarity we will get when we are looking at the field signatures of such features like related to the normal fault and the reverse fault. But in this case what you have, this is your hanging wall and this is your foot wall. So foot wall is usually what we say is the stationary wall, and the movement is been experienced by the hanging wall, and the movement has taken place. This block has moved down with respect to this one. So this is in case of the normal fault, and then if you look at in the reverse fault is exactly the opposite. So you have this one is the hanging wall and this remains the foot wall. So this again, so in previous one what we see, if suppose we consider that this was the scarp or the feature which was been formed at the surface. So after erosion you will see something like this, and in the next one again if you look at, then what you will be able to make out clearly is very much similar to what we have seen in the previous slide. So the point is that in both the cases, the feature on the surface, that is your fault scarp, will be very much similar in both the cases. Okay. So if you are having reverse fault or the strike slip fault, the fault scarp will be very much similar. So for detailed study, for classification or characterization whether it is because of the normal fault or the reverse fault, then you need to see the section. So stratigraphic section will be important to finally justify that whether this fault scarp is related to the normal fault scarp or a reverse fault scarp, or the reverse fault. Okay. Now this is another one which shows so clearly that there is a displacement at the greater depth, but near the surface this deformation is been seen, but there is no displacement. So fault has hasn't seen the surface, and this type of deformation, what we call, is just the folding. So this has also been termed as fault related folding. And since the displacement is not coming right up to the surface, you should remember that there is displacement is not coming right up to the surface, but deformation do. So we see deformation which is coming right up to the surface. The flat surface has been deformed along a reverse fault, but no displacement has been seen here. Hence such type of faulting is been termed as, or the deformation is termed as, either along the blind reverse fault or a thrust fault. Okay. Now there will be a combination of both. So the initially what we have looked at is, one is your strike slip fault and another one is reverse, or you can say thrust faults. So these are the two different type of faulting you can see, and then the combination or the third one is your normal fault. Now in this two figure, if you see 1 and 2, then what you are able to see is the combination of the first one is the combination of this one. Okay. This is your 1, and then second one is the combination of the strike slip and reverse fault. So the block has moved along the strike as well as along the depth, and block has moved along the strike. Here the block has moved down and along the strike of the fault. So lateral moment as well as dip slip moment is there. Here also there is a lateral moment as well as the dip slip moment, but here the block has moved up, and in such cases what we characterize this type of fault are termed as your oblique slip fault. Okay. So slip has occurred obliquely. Now one thing which you should remember, that the direction of the dip, okay, the dip plane, if you see, is in both the cases, either it is, this is of course the normal slip is also there along the strike slip, but if you just consider the normal slip, then the dip of the fault is in this direction, and in the reverse dip slip, the dip of the fault is in this direction. So any block sitting on the top of the inclined plane will be your hanging wall. So this you will have to remember. So further what we see, we have the displacement in this direction, and in this case the displacement is, so we have lateral as well as dip slip moment along the strike and along the dip of the fall. So basically if you consider all these three type of falls, strike slip fall, reverse fall, normal fall, and what you see is the oblique slip also. So this clearly suggests that we have a very complex phenomena or the process which is taking place in nature. And the part which we discussed in the beginning, that we look at the global tectonics and then we come down to the regional and the site specific. Now to some extent the global tectonics and the regional tectonics will help us in at least having a preliminary interpretation or inference that what type of deformation we will see in a particular region. So in case of extensional tectonic environment, we'll see of course the two plates are moving away from one another, so we have mostly the normal faulting we will be able to see. But in case of the transform deformation along the transform fall or the transform fall boundaries, we will see that two plates are just passing each other, and in case of the compressional tectonic environment, we will see mostly the reverse and thrust fault. But nevertheless you will come across at many locations the oblique slip depending on the orientation of your maximum stress axis. So you will find mostly even in the compressional tectonic environment, mostly you will find the reverse and thrust faults, but along with that you will also come across the oblique slip faults. Now this part we have already discussed in the beginning, that whenever there is faulting you will have earthquakes, and further the earthquakes usually we are tagging them to the active faults located in seismically active regions. Now knowing or mapping the active fault, we should understand that what is the surface expression of those active faults and related deformational features. Okay. So basically what we say is the active fault topography. So as we have discussed in the previous lecture, that we have the earthquakes, we are relating the earthquakes with the active faults, and the active faults are the locations or the weak zones which are likely to produce the earthquake, large magnitude earthquake in near future. And we also talked about whether they are whether we can classify that as an active, that depends on us, active, potential or capable. Now whatever the deformation will occur along this type of faulting, either it is in strike slip environment or reverse compressional tectonic environment or normal, it will be seen on the topography. So for us the active fault understanding of active fault topography will be extremely significant. So earthquake is caused by rapid movement of fault in subsurface, and the surface manifestation, what we call rupture, that is a displacement in the subsurface, often reaches the surface when the earthquake magnitude is around 7 or greater than 7. So what does this indicate clearly? That the earthquake with moment magnitude less than 7 may not result into surface rupture, but this postulation is not exactly correct, because in some cases we have seen that even the displacement has not reached right up to the surface, but we had a big earthquake like large magnitude earthquake. And the best example if we see is magnitude 7.6 of Bhuj earthquake. The deformation reached the surface, but this displacement did not. So again, such blind earthquakes are there around the world, which have occurred in recent past, and that has resulted into a sort of a challenging job to identify the active fault. Now, usually what we take is the topography. Okay, that is what we are talking about, the surface expression. So, when there is a fault that reach surface, that is due to the displacement, we will categorize that as an active fault, but this is in narrow sense. Okay, but we can see, as I was showing in one of the slide, that you have the displacement remain subsurface, but the deformation reached right up the surface. So, with an understanding and knowledge of those features, we can also classify that whether this is related to the active fault or not. You may not able to see the displacement in section also, but at least fault related folding which is coming or the deformation coming in form of folding at the surface should also be taken into consideration, and the associated landforms will clearly tell us whether there is a deformation in that area or not. So, in strict sense, if we say that we will consider the faults as an active fault only if we see the surface topography or the displaced surface, then that may not be completely true. So, in narrow sense, we can say that okay, fine, whatever the displacement which is reaching right up the surface along the faults are termed as active fault. So, this is basically the idea behind what we were talking about, that we have like medium magnitude earthquake or large magnitude earthquakes, or we can say moderate and large magnitude earthquakes. So, everything depends on the amount of energy and at what depth those earthquakes have occurred. Okay. So, these are the three examples which have been given, that you have surface ruptures in case of the small magnitude, intermediate magnitude and large magnitude earthquakes. So, again, as I told, that this it depends on the energy released and the displacement at what depth this type of earthquakes are occurring. So, in case of the small earthquake, mostly the surface rupture will not be seen, no fault on the surface will be seen, hence it remains blind. So, you may say that the earthquake which took place, as I told the example of 2001 Bhuj, was magnitude 7.6. So, even it was a large magnitude earthquake, then why it did not reach the surface? Okay. The reason could be that the energy was not sufficient enough to displace the material in that region. Okay, that may be one of the reason. But here if we basically consider this three, that is small, intermediate and blind, then in case of intermediate we will see some deform or displacement which is coming right up to the surface. So, obscure fault topography will be seen, but in case of the large earthquake, that what we were talking in the previous slide, that if you are having the magnitude MW greater than or equal to 7, then you will have the surface rupture. So, in this case you will have clear surface rupture. Now, what it has been shown here, that we will even with that you will have the larger area which will be covered in terms of the rupture area, because rupture area will include the length as well as the depth. Okay, so the whole area along on the fault plane. So, intermediate you will have less portion which is getting displaced, but in case of the large you will have larger area which has been covered. So, this again put us in a challenging situation to identify the active fault in the region, but nevertheless with the help of detailed topographic interpretations or the morphological studies of the landforms, we can easily make out that which area is active and where are the active faults located. Now, what is active fault mapping? So, active fault mapping is to look for fault topography created by ancient earthquakes, like fault scarps, warped, folded surfaces, pressure edges, back tilted surfaces, offset and deflected streams and ridges. This all forms the part of the geomorphology, and further, as we will move into the respective domains like compressional tectonic environment or strike slip faulting environment and normal faulting environment, we will learn more about the individual fault topography developed with respect to the different tectonic regimes like strike slip, compressional and tectonic, and normal or extensional tectonic environment. So, in general, what we will do is, we will in this lecture will try to quickly look at few of the examples just for the introductory purpose, that what exactly is the fault topography we are talking about. So mapping, usually we take into consideration the first step is the aerial photo interpretation. So, if you are having the high resolution aerial photographs, or you are having the high resolution aerial satellite data, that can be used for interpretation, and is the most basic for the technique for the active fault mapping. So, this is the first step. But as I told that we will also look at that what are the different landforms, tectonically formed landforms in different environment. This we will slowly learn in coming lectures. Okay. So, we cannot detect any active faults without satellite aerial photographs or high resolution satellite data, especially on active faults unreported by historical documents. Okay. So, if this suggests that if we know that these are the active fault regions, then you will be easily able to pick up the active fault. But if there is absolutely no evidence reported, okay, evidence might be on occurring or lying on the surface, but if there is no report of an active fault in any region, then it will be difficult eventually just locating, going in the field. So, the aerial or the satellite photo interpretations or the satellite data interpretation is extremely important. So, in particularly for active fault topographic mapping or active fault mapping, we use satellite photo interpretations. We also take into consideration the literature, and this literature mostly will be related to your ancient or historical chronicles, and that will help us at least to some extent to know that which area hosted large magnitude earthquakes. Then we do field surveys, selection of the trench sites, trenching investigation, then collecting the dating material, identification of paleo earthquakes, then comparing those paleo earthquakes which are identified from the trench investigations will be compared with the historical data available, and finally this goes is one of the component for seismic hazard assessment based on the time predictable model. So, we saw in one of the slide that one block is moving up and another block is remaining stationary. Now, with this you can easily make out that if there is a displacement, there will be a development of the topography. So, even if the displacement does not reach right up to the surface, you will be able to see the topography which has been developed. Okay. So, this is there is a fault here. So, you are looking at the section and you are looking at the topography also. So, you have the deformation which has occurred along this fault. There is the fault plane here, and a net displacement, if you want to measure, you can easily measure this. I have already discussed in one of my slide before. So, you have this is your net displacement. And what you see is the topography which was been resulted because of this one. Okay. So, I will stop here and we will continue in the next lecture. Thank you so much.